We'll start this video by talking about another kind of example of an R module. So we know that if we have a ring R, we can build many other rings out of R. For example, by taking quotients of R modulo ideals. So let's suppose that M is an R module. And for some two-sided ideal, okay, so now we're not necessarily in the case where R is commutative. So for some two-sided ideal, I in R, we have that A dot M equals 0 for all A in I and M in M. So, okay, so what's going on is we have an R module. So we have an action of R on M. And we're saying that when we act by anything in the ideal I on any element in the module M, we get 0. Then we say that M is annihilated by I. In this case, we can make M into an R mod I module. So not only does M have the structure of an R module, but it also has the structure of an R mod I module, where R mod I is this other ring that is related to the ring R. So how does this work? We have to say, how does an element of R mod I act on an element of M? Well, what does an element of R mod I look like? It's a coset of the ideal I in R. So it looks like R plus I for some R in the ring. All right, so what do we want R plus I dot M to be? It'll be R dot M. And this will be defined this way for any coset R plus I of this quotient ring and any M in the module. Okay, so we have to check that this is well defined, right? So that this doesn't depend on a choice of coset representative. And you can do this by saying, okay, if you have R plus I equals S plus I, if R and S are in the same coset of I, then how are they related? Well, S has to be equal to R plus something in the ideal. So S equals R plus A for some A in I. So then what is S plus I acting on M? Well, it's S acting on M. And that is R plus A acting on M because S is equal to R plus A. And then using the distributive law, one of the module axioms, that is R dot M plus A dot M. But what's special about this ideal I is that we know that A dot M equals 0 for any A in I and M in the module. So this just is R dot M. Okay, so if you pick a different representative for the coset, you still get the same elements of the module M. Okay, so this is well defined, but then you need to actually check that this turns M into an R mod I module. So you have to check these module axioms. So what are those? You have to check that the action is compatible with multiplication in R mod I. So this property that R dot S dot M is the same as R times S dot M, where now R and S are elements of this quotient ring R mod I. You have to check both of these distributive properties. And then if R has an identity, if R is a unital module, then R mod I also has an identity. What's the identity? It's the coset 1 plus I. And you need to check that the identity of R mod I dot M is always equal to M. And each one of these things is straightforward to check. The fact that these properties hold, where you have R and S being elements of R mod I and M being any element in your module, follow directly from the corresponding module properties. The fact that M is an R module. Okay, so this is a general setup where if we have some R module M that's annihilated by I, then we can give it the structure of an R mod I module. What are some interesting instances of that? When R mod I is a field, M is an R mod I module. It's a module over that field. So it is a vector space over the field R mod I. And what does that mean? When is R mod I a field? That's exactly when I is a maximal ideal of R. But now, in order to talk about this result that R mod I is a field, if and only if I is a maximal ideal, we want to be in the case where R is commutative. So if R is a commutative ring and I is a maximal ideal, then M is a vector space over this field R mod I. So I'll pause and erase, and we'll talk about some examples of this general construction. Let's look at an example. Let's suppose that A is an abelian group of order M. Okay, we know that Z modules and abelian groups are the same thing, so that A is a Z module, and M.x is 0 for all x in A. So what does that mean? More than just M.x is 0, but R.x is 0 for all x in A and all R in the ideal MZ of Z. So not only is M.x 0, but 2M.x is 0, and negative M.x is 0. So what does that mean? A is annihilated by the ideal MZ of Z. So what we've just talked about shows that A is a Z mod MZ module. Now let's think about the particular case where M is prime. So pick a prime number P and say that A is an abelian group such that P.x equals 0 for all x in A. So okay, as a Z module, I keep saying P.x, R.x, but really this is the same as the exponential notation like x to the P, or x plus x plus x plus itself P times. Okay, so in this case, A is a Z mod PZ module, but Z mod PZ is a field. So A is a vector space over the field Z mod PZ. Which finite abelian groups are we actually talking about? So which finite abelian groups A have this property that P.x equals 0 for all x in the group? These are exactly the finite abelian groups of exponent P, which are the elementary abelian P groups that we talked about in Math 206a. So this is Z mod PZ cross Z mod PZ cross 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 Z mod PZ n times, which you can write with this notation Z mod PZ to the n. So what's true about this group? It is a vector space over the field Z mod PZ, and in fact, it's an n-dimensional vector space, and we'll talk about dimension much more later. And if you think about it, how do you think of an element of Z mod PZ cross 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 Z mod PZ? Well, it's n tuples of elements that are in Z mod PZ. So this is exactly the same as the affine n space over Z mod PZ from earlier in this lecture. Okay, so now that we've talked about this idea of you have an R module M and an ideal I that annihilates M, then M gets the structure of this R mod I module. There's a different way to think about quotient rings and modules. So if R is a ring and I is an ideal of R, then the quotient ring R mod I is also an R module. So what is the action of R on an element of R mod I? Well, an element of R mod I is a coset of the ideal I. So we're going to define R dot A plus I to be the coset RA of I. So this is for all R in the ring and A plus I in R mod I. And it's straightforward to check that this actually does turn R mod I into an R module. So what have we seen? We've seen that R is a module over itself, and that its submodules, or its left R submodules, are the left ideals I of R. So I is a left R module. And here we're seeing that R mod I is also a left R module. So it's a little unclear if the right thing to do is think about all R modules together, because Ideals are left R modules and quotient rings are left R modules, but these are very different things. I mean, for example, if you have a ring with identity, the quotient R mod I is a subring, like still is a ring with identity. But an ideal, a non-trivial or a proper ideal, never has identity. So these really are like different things. So I wanted to bring this example up because we've now seen back to back that if you have M being an R module, if you have an ideal with certain properties, you can think of M as an R mod I module. That's very different than thinking of R mod I as an R module. So one of the things that's difficult about first learning about modules is that they're really, it's a big language that encompasses lots of different kinds of examples. So at first, it's possible to get some of these different kinds of examples confused with each other. OK, so I'll pause and erase, and I'll just talk about a few final examples. We'll finish this lecture with two last examples. So let's say that R is a commutative ring with identity 1 not equal to 0. And let's let M be the polynomial ring R bracket x. Then M is an R module. So we have to say what the scalar multiplication is. We'll define R dot F to be the product of R and F in R bracket x. So how are we multiplying an element of R and an element of R bracket x? Well, R is an element in R bracket x. It's a polynomial of degree 0 in R bracket x. So we'll just take this multiplication in R bracket x. So it's straightforward to check that M really is an R module here, and you should check that. One more example. Let's say that R is a commutative ring with identity 1 not equal to 0, and let's let M be the set of all functions from R to R. So we want this to be an R module. So how are we going to add functions? We'll add them pointwise. So what does that mean? If you have two functions f and g that go from R to R, you can define f plus g by saying what does it do to every x in R. So it'll be a function from R to R. And we'll say that f plus g applied to x will be f of x plus g of x, where now this addition is taking place in the ring R. And we have to define what scalar multiplication is. So what is the function from R to R given by R dot f? Well, what does it do to each x in R? R dot f applied to x will be R times f of x, where now this multiplication is happening in the ring R. So R is an element of the ring. F of x is an element of R as well, because f takes an element of the ring to another element of the ring. OK, so you can check that this is an R module. And this example is so general that it's maybe not that interesting. But the key idea is that if we oppose additional structure on this set of maps from R to R, not just taking all functions, but maybe functions that have nice algebraic properties, then we'll get interesting examples of R modules.